Okay, Octave and MATLAB also have several functions available for finding the zeros of a function or finding the minimum or maximum value of a function. So let's actually look at those features. First, finding the zero of a function. So we used the roots equation book previously to find the roots or zeros of a polynomial function. The FZero function will find a solution to the equation fs equals 0 for an arbitrary function f. It doesn't have to be a polynomial. A couple of things about the FZero function though. The way it works is it accepts a function name as its first argument. And there are several functions that do this in MATLAB and Octave, but this is the first one that we've looked at. And in this case, we want to find the zero of this particular function, cosine of exponential of x plus x squared minus 1. So we put that in a function file. You can call it anything. Again, you have to make sure that the file name and the function name agree. Okay. It can only accept a single argument and it returns a single argument. And that has to be in vector format. It has to be set up so that if you pass it a vector, it returns a vector of the same length. And so notice here we're using element by element operations here when we actually square x here. But this can be an arbitrary function, anything you might dream up, and then we pass the function name as an argument to FZero, and there's two syntaxes for doing that. Two ways to do that. You can either enclose the function name in quotes, single quotes in MATLAB, single or double quotes in Octave, or the other way, and this is the syntax I prefer, but it's your choice. Just put an @ symbol in front of the function name. And this tells MATLAB that this is actually a function. So what FZero does is, it searches through this function using this second argument as an initial guess, and will search for a zero starting the closest zero closest to this initial guess and return that value of x. So let's look at an example here. So I've actually typed in the same function, called it myfun. It's in the file called myfun.m. Okay, and then here I call FZero two different ways, using the function name in quotes and also using the @ symbol. They both these should return the same value of x. And then I also plot the function. And I call FZero with an initial starting argument here, and we'll see the purpose of that in just a second. But plotting the function gives me, a lot of information about it. So when I run this script, okay, it found a 0 at 1.33. Okay, both these methods return the same 0. So here's what the plot of that function looks like. It's a little bit crazy. So of course, FZero solves for when this function is equal to 0. We see the function actually crosses 0 at two different points. And also another thing to notice is as I move my cursor around, I get the x and y locations of the cursor. And I can see that there is a 0 crossing right at about this point, close to the 1.3. Okay. And then, the function value is close to 0 there. Of course, what Octave returned from the FZero function is that 0 crossing is at 1.3367. I could also, display the value of the function at this location. That should be 0. So if I run this again, I get for y, I get a really small number. It's not exactly 0, but it's 5 times 10 to the minus 15. It's very, very close to 0. So, Octave did a really good job of coming close to finding the 0. And so this is the 0 I found with the starting guess of 1. From the plot, I can see there is another 0 though. Back here, close to, according to my cursor, it's actually close to about -1/2 or 0.45 is what's showing up here. So if I give it a different starting value of -1, it finds the other 0, and that's at negative 0.44. Okay. So there's some other functions that take function arguments, so that it's handy to know how to use this notation. In particular, we'll look at some functions for finding the minimum of a various function. So fmin bound finds the x value where a minimum occurs within a particular range between x values of -1 and 2. It'll find where the minimum of that particular function in that range. Again, you can either use and close the function name in quotes, or use the at notation. Or with fmin search, you give it an initial guess, but it'll look for a minimum close to that point. Again, it may not return all minima in the function. That's going to be dependent on the starting guess. So often you'll want to plot the function to get some idea of what it looks like. Let's see what I have here for. So it's the same function. We're looking for the minimum location between -1 and 2, and then we'll evaluate the function at that location. And then here's using min search. Okay, and then I call it again with a different bound. So let's see what happens here when we run this. Okay, it's finding, and let me look at the plot again. It found a minimum near 0.8. So again, now we're finding a minimum of the function, not the 0, what FZero did. Now we find a minimum at x equal about 0.845, and then the corresponding y value is -0.97. And then the fmin search with that starting value actually found the same minimum. I also called fmin bound with a range between 2 and 2.3. Let me call back up the plot here. And so here's 2 and 2.3. I can actually force it to look for a minimum within this range, and that minimum location is at an x value of 2.1874. Okay, so so here I've used a function file, but the function was really simple. It was just a single line of code. Seems like a lot of extra work to go through the process of actually writing a function file to do that. So there is alternate notation for doing for specifying a function which it's a really simple function. Let me illustrate that. Okay, now it uses this kind of strange notation at x, and then here's the rest of the function. This is what's called an anonymous function, and I assign this to a variable f. Now after this assignment, I can use f just like a regular function, f of 0, for example, or f of 1, and I can pass it to any of the functions that find zeros or find minima. So if I run this function, I get the same values that I got before, where I had this thing defined in a function file. Now I prefer to actually assign. This is what's known as an anonymous function. Here I'm assigning it to a variable, so I can use that variable name, then that variable, to represent this anonymous function and other function calls. You could also just pass this directly as an argument to a function, and that's what's shown here on the slide. And I usually like to take the extra step and assign this equal to a variable and pass the variable, but you don't even have to do that if you want. You can directly pass the anonymous function. You can write anonymous functions so that they have multiple input arguments like x and y. Just extend the notation to be x comma y, and then the function here would then also have to use the variables x and y. And then of course the variable doesn't have to be x, it can be whatever you want to call it. Okay, so anonymous functions and knowing how to use them is a really useful skill. We'll see that when we start actually looking at integration, those functions also take these function names as arguments. And there again, if you're dealing with a simple function, it's easier to embed the function right in the script as opposed to having to write another function file just for that simple function. There are some other optimization toolboxes available or packages available for Octave. We're not going to talk about not going to talk about these. These are some more advanced mathematical methods. So in this exercise, you're asked to find the minimum of this particular function. I have no idea what that looks like without plotting it, in the range between minus pi to pi. So again, if you want to, and then you're asked to plot it. So if you want to try this, I'd recommend trying this using an anonymous function approach. Pause the video, try and run it from Octave. Okay, so here's what the solution looks like. Actually, let me call that up. Okay, so here I did that with an anonymous function. Typed it in using the element by element multiplication notation here, so that if x is a vector, the return value will be a vector. So I didn't put the function in another file, although you could have. Here I just assigned the anonymous function a variable. Sometimes this is called a function handle, an Octave notation, and then now I just use f here and pass f to fminbind to look for the minimum. And then also notice how I use the same function f of x as I pass this to the plot command to produce the plot. I also use the line function to actually plot a line at the minimum location. So when I run this, okay, a couple things. It finds a minimum at 0.776. Okay, and let's actually look at the plot. It found a minimum, but we actually see there's a lower minimum in this range from minus pi to pi. But it didn't find that particular minimum when I ran the function. When I ran this function, it will return a local minimum, but it doesn't necessarily find the global minimum. I can restrict it, if I put the range from like -1 to 0 instead of from pi to pi, it will probably find that other minimum. So let me try that. Run this again. Found a different minimum. And if I show the plot, I'll see, oops, didn't find that one either. It found this other one. So let me actually restrict it again from maybe minus 0.5. Let's see what it does this time. If I look at the plot, yay, that time it actually found the global minimum. It's located at an x value of 0.126. Actually, if I call f with that, what is x? Oh yeah, I redefined. It's x min. F of x min is the negative 0.75 value. So that should be the value of that function at that minimum location. When I put my arrow there, my cursor there, I see it's about a negative 0.1 and then a y value of negative 0.7. Of course, that agrees with the results here, negative 0.1 and negative 0.7. Okay, so that's it for this section. In the next section, we'll look at differentiation and integration.